Hello, my dear student. Today we are in lecture number 33. Okay, it is lecture 33 of chapter 3, that is current electricity. Current electricity. Okay. Uh, my dear student, we have covered in last lecture about the drift speed. That was the average speed or the average velocity attained by the charged particle, that is a charge carrier within the conductor. Today we will derive a relation between, or here the represent the relation between electric current and drift speed. Okay, so the first topic we are studying today, it is the relation between electric current and drift speed. Okay, my dear student, so already we have studied about the drift speed and we know about the electric current. Directly we are going to derive the relation. In 3 marks or 2 marks, you will be asked in examination to derive this one. Suppose the electric field is given. Here, few things you must remember. L is the length of the conductor sample. A, cross-sectional area. L is the length. A, cross-sectional area. Okay. L is the length. And one thing which is very important, suppose the number of charge, that is the electron, are n. N is the number of charge, and small n, here small n, it is the charge density. You can say the number charge density, and what is it? So it will be the number of total charge per unit volume. Okay, the volume of the sample of conductor. What will be the volume of this conductor? Actually the volume will be A into L. This will be the volume. A, if it is cylindrical, then cross sectional area is A and length is L, so the volume will be N. It means you can write this N as N, that is the number of charge per unit volume. It is A times L. If you wish to find the number of charge, then N can be written as the small n A into L. Remember, this N is the number charge density, A cross section area, L is the length, and N, what does it mean? The N is total number of charge in conductor sample. Okay, now we are moving towards the relation between that. As we know that I is equals to Q by T. Okay, we know very well. Now this Q is number of charge times E. Q equals to NE. Using quantization, we know that. There we used to represent by a small n. It doesn't matter. You have to understand what this n is actually. So n is the number of charge and E is the electron. So the Q by T, it is the time T. Okay, my dear students. Now we have already obtained the value of n. So we can place this n as n a l, okay, into E are divided by T. Now look at carefully, my dear student. The total length of conductor the charge has to travel, it is L. Okay, this L, as we know that the charge will not move in a particular straight direction. It goes randomly here and there, and due to the number of collision it takes a time, and the time to reach from here to here, the average time, that is called the relaxation time, we used to represent by the tau. Then this T can be written as the tau. Okay, and this equation will be I is equals to NALE over tau, and This L over the total distance has to travel how much? It is L. That is, the charge has to drift by L. Then this I can be written as the N E A, and this L by tau, that is the length by time, will be the speed, and that speed is nothing but the drift speed. So this is the relation between current and drift speed. I is equals to NEAVD, and this is the relation. Okay, my dear student, this is the relation between electric current and drift speed. I equals to NEAVD. Okay, now we can take a simple example on the basis of this drift speed, my dear students. Okay, this will be your home assignment. You will try to solve by yourself, my dear students. Kindly note down the data I am giving you. Calculate the drift velocity of electron. Calculate the drift velocity of electron in a silver wire. Write down carefully. Calculate the drift velocity of electron in a silver wire having cross-sectional area 3.14 times 10 to the power minus 6 meter square. Okay, I'm giving you the data. The cross-sectional area, how much? 3.14 times 10 to the power minus 6 meter square. This is the cross-sectional area. And carrying a current is given. How much? It is 20 ampere. Okay, 20 ampere. What you have to calculate? You have to calculate drift velocity of electron, and it is the silver. I am giving you certain value. Atomic weight of silver, you know that it is 108. Okay, density of silver, I am giving you the density. This is the density, remember, and you know that density will be 10.5 into 10 to the power 3, 10 to the power 3 kg per meter cube. This is the density of silver. Okay, and the rest thing, that is the Avogadro number you need to be used, and the charge on electron, okay, you have to use by yourself. So this will be your homework. You will show me in the next lecture. Okay, so this is a simple question that you have to solve. Now my dear student, we will move for the next topic, and it is the current density. Okay, my dear student, is it the current density? What does it mean, the current density? I can wrap this one. Kindly note down. Current density. We used to represent this current density, my dear student, by symbol J. It is a vector quantity, remember? It is a vector quantity. Now, we know that it is not necessary that conductor will have of uniform cross-sectional everywhere. Suppose this is the cross-sectional area of any conductor. This will. Okay. Now, current start moving. Current is flowing I. Remember, current will be constant throughout. Whatever may be the here dimension, current will be constant. Suppose cross-section area here A1, here it is A2. What will be happen? In this particular cross-section area, and in this cross-section area, the number of charge crossing particular time, it is will change. It means the density at this point and density at this point will be different, and that is considered the electric current density. If you want to write the definition, you can write the current density. Definition of current density: it is the electric current per unit cross sectional area. Okay, so J is nothing but the current, electric current per unit area, that is the cross sectional area, ampere per meter square, and this can be written as J is I by A. Now, my dear student, we can write this equation with another relation also, as we know that I, we have already studied, it was drift speed. With the drift speed it is NEAVD over A will be cancelled out, so J, that is the current density, will be written as NEVD. So this is the current density and drift speed. Okay, so if you will be asked to write the current density or define the current density, in this way you can represent the current density. Remember, here I is constant through this conductor. If this I is constant, it means this current density inversely proportional to the cross sectional area. Okay, my dear students, if this is vector quantity, area is also vector quantity, surface perpendicular, then I, if this is the conductor, okay, if this is the conductor and this is the surface area vector A that we have studied in Gauss law, okay, then, and this is the current density if it is the perpendicular, then J dot A will give you the current I. Remember, this is the vector form, which is not very tough, it is very simple to understand, my dear student. Okay, now a very simple question I'm giving you to solve on the basis of this particular relation, that is the current density and relation between the drift speed. So write down the question and data, my dear student. An electron beam has an aperture, you know, aperture, that is the cross section area or the length of the conductor. Length means diameter of the conductor. So the question is, an electron beam has an aperture of 10 to the power minus 6 meter square. Aperture is 10 to the power minus 6 meter square. Of course, this aperture actually giving you the area. So I'm writing here the data. This will be your homework. So the aperture is 10 to the power minus 6 meter square. Now, again I'm telling the question. An electron beam has an aperture is 10 power minus 6 meter square. The total number of electrons moving through any perpendicular cross section per second is 6 into 10 to the power 16. How many electrons are crossing? 6 into 10 to the power 6 into 10 power 16 electrons. Okay, 6 into 10 to the power 16 electrons. Okay, these electrons are moving. Remember, this is given in per second. Calculate the current density in that beam. You have to find current density in that beam. Okay, my dear student, so this is your question and you have to solve using the this particular derivation with this formula. Now we'll move to the resistivity and conductivity, my dear students. Okay, what is the resistivity and conductivity? This is the very important segment, because using that particular segment we'll move to the Ohm's law. Three form of Ohm's law we will study, okay, in Ohm's law section, that is today, my dear student. So we are proceeding from current density, the formula that we have derived, current density, will proceed from there and will approach to resistivity and conductivity. Resistivity and conductivity. Okay, resistivity will use to represent by rho, conductivity will use to represent by sigma. And one thing, the relation you must remember, the conductivity and resistivity are reciprocal to each other. That is, the rho is reciprocal to sigma. So rho is equals to 1 by sigma. This resistivity and conductivity will give you the two different quantity that will help in Ohm's law also. Okay. Now, as we know that, my dear student, as we know that J is equals to what we have derived, NEVD. Okay, the relation between J and drift speed. And we also know that drift speed, it is E tau by m. So J can be written as N E, and VD it is E tau by m. Can we write? Yes. So it is N E square. Okay. N E square and tau E by m. This is the current density. Okay, my dear student. Now look at here carefully. This quantity, this particular quantity, okay, this one, N E square tau, N E square tau by m, this is called N square tau by m is called conductivity, which is the sigma. This is the conductivity, and reciprocal will be the resistivity, that is m by n e square tau, and this is the resistivity. Now the one another very important relation we obtained here, if it is conductivity, then J can be written as sigma into E, and if it is 1 by rho and it is J, then E can be written as rho J. Okay, then you have to remember this formula, and every morning you have to just memorize E rho J. Okay, you have to study this rho J, E rho J every morning. E rho J equals to rho J, that is the rho density, sorry, but the resistivity, and J is the density, that is the current density. And this particular equation is called modern form. This is the modern form of Ohm's law. Modern form of Ohm's law. Okay, this is the modern form of Ohm's law, my dear student. Now, about this resistivity, let me talk in a very simple word, because we have to use this resistivity later on. My dear student, this resistivity, actually you can see this resistivity depend upon m, that is the mass of electron, charge carrier, n, it is the number charge density, e, it is the charge of electron, and tau is the time of relaxation. My dear student, you can see if this is the conductor, this is a very important discussion, try to be focused. If this is conductor, then this rho not going to be changed by the length. If you will increase the length, remember this m will not change. This is the m, that is the mass of individual electron. Of course, by increasing the length, you cannot change the mass of individual what? Electron. Now n, the number density is not going to be changed. How the density will change? This density, the number of electrons per unit volume. If you will stretch, if you will change the length of the conductor, there will be the more electrons within that conductor sample. It means it is also not going to be changed. E is the charge of electron. It means this is also not depending. It is not depending upon m. It is not depending upon n. It is not depending upon, this is not depending upon E. And what about the tau? So you will see it depends upon tau, but there is certain limit. how this tau will change the resistivity. Remember, it is quite clear. If you will change the cross-sectional area, whether this rho will change, cross-sectional area you will change, whether the rho will change, the answer is no. Cross-section area if you will change, then if you will cut this conductor in two parts, then what will happen? The equal density will divide in two parts. E not going to be changed. Okay, so everything is not going to be changed. It is quite clear rho is independent from the dimension. Rho does not depend. Okay, does not depend upon dimension, which is very important. What are the dimension? Actually, the two physical quantity will study in the dimension length and cross sectional area. So the resistivity not going to be changed by changing the length or cross sectional area. Now the last thing was the tau. Okay, this relaxation time, whether this is depending on the relaxation, the answer was yes. But how this relaxation time will change? Okay, by changing the length or cross sectional area you cannot change the relaxation time. Relaxation time will change by changing the temperature. If you will change the temperature, this relaxation time will change. It means it depends upon temperature. Yes, so the third quantity, temperature, and on this temperature this depends. Okay, so it depends upon the temperature. It means relaxation time will change and the resistivity will change. If it means the resistivity depends upon temperature. If material will change, of course the number, density, everything will change. That's why the resistivity will change. So these are the factor on which this resistivity, my dear students, depend. That we have studied already in standard 10, but minutely I taught you over here. Now my dear students, what is this resistivity means? So the resistivity, it means, remember, in the very simplest definition, and this resistivity also called, remember students, this resistivity also termed as specific resistance. Specific resistance. Resistance we'll study in very detail later on. This is also called the specific resistance. And my dear student, resistivity is nothing but the resistance itself, resistance of elemental part of the conductor. Resistance of elemental part, that is the smallest part. If you cut this conductor with the very smallest part, and resistance of that smallest part is considered as the resistivity. If it is the smallest part, it means it is not going to be changed on the length, because if that already smallest, then you cannot change the length. If that is already smallest, then you cannot change the cross section area. It means, of course, again we are getting, it is not depending upon the dimension. So the resistance of elemental part of the conductor is considered as the resistivity. You will find another definition in your books, in your course books, that is the resistance of the unit length and unit volume cross section area of any conductor is called the resistivity. But the fact is, the resistance of the elemental part of any conductor is the resistivity. Now my dear students, will move for the further topic. Now here we will see the atomic form of Ohm's law, my dear student. Okay, atomic form of Ohm's law. Uh, it was asked last year in board to derive the atomic form of Ohm's law. The question was not written directly the atomic form of Ohm's law, but the question was written to derive the Ohm's law, or the equation of Ohm's law, using the resistivity and conductivity. Okay, so we are proceeding that derivation or the relation. Suppose this is a conductor sample. What is the length of conductor sample? Suppose it is L. Okay, and we have maintained this conductor at potential V. What does this potential will establish an electric field. Okay, so electric field is established E. Do you remember, my dear student, about the potential gradient? Yes, potential gradient, that is also called the electric field. E equals to V, that is the potential per unit length. Okay, it was L. Actually it was written E minus dV by dx. That minus sign we are using over here as the magnitude. E is equals to V by L, and we know already, my dear student. Okay, and we know our drift speed is what? E tau by m, we know na. And the drift speed, okay, if this is the drift speed, then this drift speed can be also written as, by replacing this electric field by this equation, if we'll put this electric field over here, then drift speed will have E tau by m into E is V by L. Yes, could we write? Yes, we can write. Now, my dear student, you can simplify this as uh, and comparing with the electric current. Now we know that I is equals to NEAVD. Hope you remember. Then this VD can be written as, this VD can be written as, by putting this value, or over here this put this VD in this equation. I is NEA and VD can be written as E tau V by ML. Okay, what will happen? This I equals to N E square tau by ml into V. We got a relation I equals to N E square tau by ml into V. Okay, my dear student, and this is the very important relation, and this is the atomic form, but you cannot see the Ohm's law directly over here, so I'm just showing you Ohm's law in this equation. This particular quantity, this quantity that you will study later on in your higher classes, this is called conductance, and it is represented by Z. This is conductance. Okay, and this conductance is equals to N E square tau by ml. Okay, conductance, it is reciprocal to the resistance. Okay, and conductivity will be reciprocal to the resistivity. Okay, so this is the conductance, and it is reciprocal to the resistance. Try to remember. It means you can write 1 by R, this one also. And what will be R? If you write this R, then R will be ml. If it is reciprocal, then ml by n E square tau. If you will put this value in this equation, then you can write this I as equals to, this is 1 by R, 1 by R into V. So the V is equals to I into R. So again we derive the Ohm's law using this atomic form. So this is the atomic form of Ohm's law. V is equals to I into R. And one question you can solve, my dear student, on the basis of this particular derivation. Okay, I'm giving you a question. If you wish, then you can solve this question. So kindly write down the question 1, and that will be your homework. Okay, so this is the homework. What is, write down the question. A potential difference V is applied to a conductor of length L and diameter D. This conductor I'm giving you potential how much given? V, length is L, diameter of this conductor is D. Okay, the diameter is given. How are the electric field? Remember, electric field E. Listen carefully the question. How are the electric field? Second, drift speed, that is the drift, velocity, and resistance. Okay, and third one is the resistance. The three things: drift speed, electric field, and resistance affected when. Condition I'm giving you. How these three will affected when. Condition I'm giving you. The first, V, that is the potential, is doubled. V is doubled. Okay, if V will be double, then how this three quantity will affect, you have to find, you have to show. The second, okay, if L is doubled, if length is doubled, okay, again I'm doubling the length, and if D is double, if this diameter is double, then how this three quantity will be affected, you have to find the answer. So with this homework we are concluding today's lecture, my dear students. Thank you very much.